This video is on gas stoichiometry. So first we have to figure out the number, First we have to determine the volume of oxygen at 92 kPa, and this should be 23 degrees. For some reason it didn't want to transfer over, so this is 23 degrees Celsius is required to react 1,000 grams of octane. So oxygen with a hydrocarbon. So obviously this is a combustion reaction because we have a hydrocarbon again and oxygen, and we're going to make carbon dioxide then and water vapor. So there is 9 times 2 hydrogens makes 18. There is 8 carbons, so now there's 8 carbons. So now counting over here, I have 16 oxygens in here and 9 here, so that gives me 25. So 25 is an odd number, right, that I can't put in here. So one of the best ways to do it is do 25 divided by 2 and say to yourself, okay, that's 12.5. And what we're going to do, instead of using the decimal, is that we're going to double everything so that we don't have that decimal anymore. So instead of this being 1 now, it's going to be a 2. Instead of this being 12.5, it's going to be the 25. Instead of this being 8, it's going to be the 16. Instead of this being the 9, it's going to be the 18. Now it says determine the volume, and it's telling me the pressure, and it's telling me the temperature, which of course I would have to change to kelvins. So that would be 296, and it's going to react with 1,000 grams of this. So first job is to figure out the number of moles of octane that I have by doing mass divided by molar mass. So molar mass is going to be 12.01 times 8 plus 18 times 1.01. So I get 114.26 grams per mole. Oh, I multiplied there instead of dividing. So let's try that again. 1,000 divided by 114.26. That's better. Now I get 8.751969193 moles. Now my next step is going to be to use the mole ratio. So this is 8.75 moles of octane, and we're going to need, this time, moles of oxygen divided by moles of octane. So I'm going to take the number on my calculator and multiply it by 25 and divide it by 2. And now what I'm going to do is I need to figure out the volume. So because I need to figure out the volume and I have a pressure and a temperature, I'm going to use this PV equals nRT, and by getting rid of P, right? So I'm going to use V equals nRT divided by P. So I'm going to take that 109. The R is the constant, right? So that's 8.314 that I want to use in this case because I'm using the kPa. And the temperature we said was 296. The pressure was 92. So now we're going to take the number on our calculator, multiply by 8.314, times it by 296, and then divide it by 92. And I get this number. Now, I can have 4 sig figs, so that means that my answer will really be 2,926. Oh no, I can only have 3 sig figs because this has 3. This has 3. So I'm going to have to write this number in scientific notation. So it would be 2.93 times 10 to the third liters. So 2.93 times 10 to the third liters, because I want to write it in scientific notation so that it only has 2 sig figs. Okay, next one. Determine the mass of heptane required to react with 250 liters of oxygen gas at 98.0 kPa and 17 degrees. So first off, we have heptane, and again it's reacting with oxygen, so therefore it is a combustion reaction. So we always make that carbon dioxide in the water. So starting with carbon, I have 7 on the left side, so I need to have 7 on the right side. Then I see that I have 16 hydrogens on the left side, so I need to put an 8 in front of here to make the 16 on the right side. And here I have 14 oxygens, right? And here I have 8, so that gives me the 22. So that means I put 11 in front of here, and then it should be balanced. Okay, now it says determine the mass of this. Then I need to react with a volume of this, and pressure is this. Then the temperature is 17 degrees Celsius, so we add 273 to 17, which is going to give me 290. So first thing is that I have to figure out the number of moles of oxygen. So I simply can't do this by mass divided by molar mass, nor can I do it by using the concentration and the volume, right? This time I'm going to have to use the PV equals nRT formula, and manipulating it for N, get the PV divided by RT is going to give me the number of moles. So I'm going to have 98 kPa times the 250 liters. Remember that on your calculator you should do this in brackets first. Then we're going to divide it by the R, and then we are going to times it by the temperature. So 98 times 250, and then divided by 8.314 times 290. So I get 10.16150573. Now I'm going to have to figure out the number of moles of heptane that I have by using the mole ratio. So I'm going to take the moles that I just figured out of oxygen, and I want to get rid of moles of oxygen, so I'm going to take the 11 from the valence equation and 1 from the valence equation for the heptane. So I'm going to divide by 11. Oh, can't read that. Let's try that again. So I get 0.923773248. Now I want to figure out the mass, and I do that by doing n times n. And the molar mass of heptane, so I'm going to have to do 12.01, so that's carbon, times it by 7, and add 16 times 1.01, which gives me 100.23, and I'm just going to double check that number. So 16 times 1.01 plus 12.01 times 7. Yep, so 100.23. Now I just have to get that 9 number back, so now times 100.23. with 3 sig figs, it's 92.6 grams. Great. One more question and get. Okay, so what volume of hydrogen gas at 92 kPa and 20 degrees Celsius can be produced by the reaction of magnesium with hydrochloric acid? Notice that it says excess, meaning that we have lots of it, right? So magnesium is going to go with chloride. Magnesium is 2 positive, chlorine is negative, so we'd get MgCl2, and we'd have hydrogen gas left over. This, again, is a balanced equation that we use in the molar volume of gases. Okay, so what volume of hydrogen gas are we going to make? We tell us the pressure, and the temperature would be 293 kelvins. And I think we are missing something in this question. Yep, we are missing a mass of magnesium. So we're going to say that we have 2 grams of magnesium because there's nothing for us to figure out the number of moles for otherwise. So we're going to say that we have a mass of 2 grams of magnesium. So firstly, we have to figure out the number of moles of magnesium by doing mass divided by molar mass. Let's make sure it's balanced first. I got too far ahead of myself. So there's a 2 here, so I'm going to put a 2 in front of here. That makes 2 hydrogens. Now it should be good. And magnesium is 24.31 grams per mole. Now we'd have to figure out the number of moles of hydrogen that we have by using the mole ratio. So we take the number of moles of the thing that we know, and then we times it by the mole ratio. So we have 1 mole of hydrogen and 1 mole of magnesium, so it would be actually exactly the same. But now it's moles of hydrogen. And then lastly, we want to figure out the volume. So we're going to use this PV equals nRT and do nRT divided by P. So the N is the 0.8227. We're still going to use that 8.314 gas constant because we're using kPa. The temperature is going to be 293 and the pressure is 92. Take the number on our calculator, times it by 8.314, times it by 293, divided by 92. Gives me 2.17 liters. 28, which is a lot of hydrogen gas. This was the reaction that we do again in lab where we have magnesium reacting with hydrochloric acid. Imagine if we had used 2 grams, which doesn't seem like very much, right? How much gas that would have produced. We wouldn't have had a eudometer big enough to collect it all. Great. Okay, now you should be able to do all the stoichiometry, and we're going to work on limiting reagents next.